And from here on, I want to Miguel. I'm computationally impaired, so I asked Guy to show our XMLC package.
Hi, Robert.
So.
Okay, great. So here we are. I guess the main file has been already unzipped. You need a microphone, probably. Oh, yeah.
Oh.
I think it will be okay. Okay. Yeah, don't worry. Or maybe when I.
Well, let's make it perfect. Otherwise, you're the only one. No, you do it yourself.
Okay.
I may kill you. I will see you, Richard.
Maybe too much. Okay. Hopefully it's stable.
Okay. Thanks. Don't put it on the table. Put it in your pants.
Sure. How do I look? Is it okay already? Everyone can hear me?
Maybe use the other one.
Okay. I think it will be alright. Okay. So here's the main file. It's already been the main folder has been already been unzipped. So we have many files, many folders. They are all explained. The contents are explained in the README file. So just so it's been coded so you can use it on Octave on MATLAB if you don't have MATLAB. So you just have to work on the compatibility. So first you can go to the compatibility file folder, sorry, and then you can run the adequate script. So in this case, Octave. Let's do it. If I can. On the Windows version, you just have to copy the files that are in the MATLAB Octave folder to the main folder. You just overwrite them, and it will work. So now we can go to the main folder, and then just run Octave. In this case. Okay, great. Wow.
This does machine learning control.
Now the first thing to do is to launch the initialization script to load all the paths necessary to create the MLC object that will be optimized. So here it creates also an MLC object that contains our problem, so XMLC. So the name of the run, dynamical system benchmark. The name of the run is important for saving. You can change it, for example, by so the name of the object is MLC. You can just, by default, you can create by your own. It's all explained in the README file. More details, I mean. So you can change the name, for example, for MLC.parameters.name with an uppercase, and then here just put up my run, for example. Like name is changed. And now, if you want to see again the features, MLC.show problem, the name has changed. So the problem to solve is a generalized mean field model. So the problem is in the here, the plant folder. Here you can add your own problem. So here's the generalized mean field model. So one file for the parameters. It will contain all the MLC parameters. You can look at it. And another file, the problem, which is actually our solver. Here another folder, my problem, that is a copy paste of the other one. You can modify it at will following your conveniences. So here have the number of inputs. One is going to control the the generalized mean field model. We have two oscillators, one unstable, one stable. We want to bring the unstable one to the fixed point by actuating on the stable one. So if we want, and we're going to actuate on one of the components of the stable oscillator. Number of outputs or the sensors, there are 4 for the 4 variables, A1, A2, A3, A4. So you have then some parameters, the population size, 10, and stem strategy, elitism. So we'll keep only the best individual from the last generation to the next generation. Crossover, 6%, mutation, 30%, and replications, 10%. So we're going just to show you the unactuated dynamics. Okay. options. Let me just clean this. Okay, we changed the size, but maybe a bit too much. Yeah. Anyway, so here we'll take just the parameters of the parameters to modify them. Here we have I modified just the initial condition close to the fixed point for the unstable oscillator and far from it. So 0.01, 0, and 0.25, 0.25. Here just run the solver with zero control law. This is the control law, so zero for no control law, no actuation, I mean. So all parameters, A1 for the visualization. So let's just run it.
We use micro and we should
Yeah, sure. Okay, so we have also a plot option. So we have so a plot. On the top right, left, sorry, you have the controller, 0. On the top right, yes, you have the growth rate of the unstable oscillator. So here for the phase portrait for the unstable oscillator, phase portrait of the stable oscillator. So we have our initial condition here is the red circle, here the other one. So we reached our limit cycle after we have our nonlinear saturation. And for the other one, we reach the fixed point. So we are going to use as the initial condition. We're going to use 1 point on the limit cycle and the other on the fixed point for the unstable oscillator. So I'm just going to run two generations of a population of 10 individuals, because on Octave the for loops aren't as optimized than in MATLAB. So it takes more time, and then I'll show you some other run I did earlier. So to run the optimization process, you just have to say mlc.go, and here indicate the number of generations you want. For example, 2. Let's go. So first of all, you have the populations will be generated. So this is the Monte Carlo step. We have candidate solutions generated randomly. It's optimized that new individuals are different from the other ones. Then we have the evaluation of the individuals, one by one, with the cost. Okay. Now, so no bad individuals to remove. It means that some of them can make the solver explode. So those will be excluded and new individuals will be generated. In this case, it's okay. Then we have the second generation that has been created with the genetic operators. Sorry for the. Then it's going to be evaluated. So the first one is already done because it's the one that we got from elitism. We have the cost. Then there are other ones that are already done that those have been created with replication. So just copy paste from the last generation. So we don't need to evaluate them again. But of course, there's an option that you can force the re-evaluation if you had some problem with some noise. Okay, so now this is after 2 generations, this is the cost of the best individual, which is not that great, with some control law. If we can see it by the method mlc.best individual without an s, and here you have some information and the plot. So this is not that great. Well, but we only have 10 generations that evolves through. No, 10 individuals that evolve through 10 generations. So it was expected. So here just so I have the cost, the control law. Yeah, that's it. So now I'm just going to show some other run I ran yesterday. So if you want to save your run and continue it later, you can do with the method mlc.save octave for the octave version, and then the matlab for the matlab version. You can also save octave files from matlab, but not the other way around. So you can just exchange from the other. And that's all. Well, just like this. Take In the save runs, it will create the MLC octave save. So now we want to load this one that I ran earlier. So if you do MLC dot load, where is it? Octave, and here put the name of your run. Of course, you have to be careful with the names, with the naming, not to overwrite some other runs. Benchmark.
Benchmark. Oh.
Thanks. Here it is. Okay, great. This time we have 100 individuals. We can look at the best individual. You can see that the cost is much lower. So the unactuated cost is 0.1. So here is the solution. So I run the 100 individuals through 10 generations, so 1,000 evaluations. This is what we found. So I only run it on 25 periods. Sorry for the stable one is a bit under-resolved because it's much slower on Octave. But on MATLAB, it took around 1 hour to run the 1,000 evaluations. But on Octave, on MATLAB, it's around 10 minutes. So here you have like a force on strong actuation at the beginning. Then we reach a fixed point. And you can see that at the end we have it starts again to destabilize. Of course, we should run it on a larger time window to have a proper control that sees what happens after the destabilization. Also, you can take a look at the whole individuals that have been explored with the MLC.convergence method. I take some time to create some pictures, some figures. There are some other methods you can find on the cheat sheet script. We are already there. Okay, so here we have a spectrogram of the controllers. Each column corresponds to one generation, and the color is the cost in a log scale. You can see through generations there is an increase of the of performances that takes more and more the generation, the population. Here's one of them. Here's the distribution of the components of the cost function of yes. So JA and JB. Here have also Pareto diagram and the Pareto fronts of the controllers with the color map showing the generations. You can see that the red or orange individuals are on the lower bound of the Pareto front. Against like this. Here we have two other plots. Maybe this one is less interesting. And here the distributions of the controllers through generations. So more or less the one that we saw with the jet mixing problem. Here with different colors for how the individuals have been generated. And the red line showing the best controller at each generation in the evaluation, and the green one for the median performance. And that's it. It's that easy.
So I showed you this software I use for my solving problems, writing emails, and now you also know to whom you could write your emails if you're interested in machine learning control. Thank you very much. Great presentation.
Thank you. By the way, this software will be available in the folder of the chapter, okay, of the lecture series. So you will have it. You have a question there?
Hi, thank you. I just saw just off the top of my head, that there was a Monte Carlo part in the graph. In a sense of genetics, are you playing God with some of this stuff in order to cover more area in your parameter space?
Okay, good point. So somehow you have to initialize the first generation, right? Somehow you have to initialize your first generation. And the first generation is essentially Monte Carlo. You use random individuals.
Okay.
And now the hope with the genetic algorithm is that you become better than Monte Carlo, that you are actually learning something. If you look into the book, some people claim that that the genetic algorithm is not really better than Monte Carlo. So essentially, if you take 1,000 individuals propagated with genetic programming and 1,000 individuals with Monte Carlo, then they are almost equally good. But we have strong evidence that we are actually learning something and that we are populating the minima. So the first is Monte Carlo. This is the initialization, and from there on you propagate with genetic operations.
So, what I'm really asking is, with the playing God thing, if the problem with genetic stuff is that you can basically not, unless you introduce a heavy mutation rate, you cannot spam stuff that is not in your initial parameters, right?
Of course you can.
Okay.
We are using controllers. At the moment you do a mutation, you can get arbitrary controllers.
Yeah.
I mean, the dimension of your possible controllers is infinitely large.
Okay, but mutation is random, right?
Mutation is random, yes.
Oh, have you considered playing God and saying, okay, it might be a good idea to do my mutation in feasible directions, if you will?
I like this question. So essentially now you want to replace the genetic operation by something which is much smarter. And I would ask you, please wait 3 more months and then look in archive. So we can do something much faster without genetic programming.
Maybe I have also a very quick question. I agree with you that some of the problems that you've shown are extremely complicated from many perspectives, but they have also something that makes it relatively easy as compared to others, and it's the fact that you can afford the cost of being wrong. But how about cases where a mistake can put the system in the wrong trajectory? So in this case, is it a way to put in the cost function also the cost of being wrong?
This is a very practically relevant question, and several answers. So if you know in advance which range you would never like to probe, then do the pre-testing. In fact, what we are doing here, before we evaluate a cost function, we look with some criterion if this controller is completely ridiculous. For instance, it always gives values which are 10 to the 38 and so on. So one thing is, if you know in advance which range is bad, you would exclude it with pre-testing. So you take the individual out, you replace it with another individual, so that all the individuals which you are testing are sanitized. Then another strategy, what you are doing, you can do a bit gradient search. For instance, suppose you have a controller which works, and you don't want to make a radical test, for instance, combustion chambers. You don't want to explode a combustion chamber. This is very expensive and can kill people. No fun. So what you can do now, essentially, you can identify a small variation of an existing controller, and now you can go in and you can use it more in the sense of a stochastic gradient search. So there are many ways how to be, in quotation marks, more careful and constraining your controllers.
Thank you. Other questions?
So by the way, another thing, so the actuators, when we have 2 high frequency components in our actuation, then suddenly the matrix valves don't work anymore. They're either on or off. So we want to avoid this. How do we avoid this? Very simple. So we have, after the controller, in quotation marks, another filter, which makes sure that the on phase or off phase has a minimum length. So our controller at the end is what the genetic programming suggests, and an additional post-processing which guarantees that we are not going over the limitations of our actuators.
Need to know them in advance.
Yes, yes, right. So this is where your essentially engineering experience comes into play.
I have a quick question which sounds a bit silly, but anyway, I will ask it.
I like it.
So, first of all, I would like to know how you estimate whether the system is controllable or observable beforehand, and secondly,
Controllable?
whether it's controllable or not with this kind of actuations, and whether it's observable or not with this kind of observations you use in your simulations. And second question is, to what extent this technique overperforms some methods like DPQ learning of policy gradient methods?
Good question. First of all, when you are talking about a controllability and observability, you are in a linear framework. And so by looking for nonlinear dynamics, essentially we play trial and error, and we do whatever is possible with a plant. So I would argue that if you would do linear control, then the observability and controllability space should match. You should do balanced truncation and so on. But all these type of approaches collapse at the moment of nonlinear dynamics. And the second question is very interesting because you are asking essentially, why did we choose genetic programming? So you go in the machine learning community, everybody hates genetic programming because it's so brute force, and COSA has alienated so many of the colleagues. There have been big disputes and so on. One reason is because it will work, I claim, much better than neural networks. And I can explain you why. With neural networks, you have a mapping from an input to an output, from a sensor signal to the actuation command. And now you have to, how do you train a neural network? Typically, you solve a regression problem of the first kind, a data fitting problem. So for a given input, you know already the output. So you train it, input, output, input, output. And at some point, you have an input which is close to your original input, and then you have your output. You have 1 million different coefficients, which you need to tune. Essentially, you would normally only use it for a regression problem of the first kind, data fitting. So this is why you are not using it. Now, control problem or closures is a regression problem of the second kind, a variational problem. So you have no notion of a local error. If I tell you, for these sensor signals, you do these actuations, you know nothing about the controller or the performance. And for these variational problems, you now have suddenly in a neural networks, maybe 1 million parameters to tune. How are you going to tune these 1 million parameters? Impossible. So I would claim the niche application of neural networks is fitting problems. For instance, you can nicely use them for modeling. If you have a dynamical system and you know for your state, your derivative of the state, wonderful, apply it. But if you have a variational problem, a control problem, or a closure problem for that case, then there are other techniques. And at this point, genetic programming is the most powerful tool which we have found.
Thank you. So I propose we go for lunch, and we come back more or less, let's say, at the same time as agreed. So 13:45. Let it be 13:50 max. Okay. Thank you.